if this is our linearized equation, and it looks pretty linear on this transformed set of axes, where are we going to find the initial height in our linearized equation?
On the y-axis?
On the y-axis where?
Where the line directly intersects y.
Sure. Our initial height, so one way to think about it in context is that our initial height is the height at which our object is at time t equals 0. And when t is equal to 0, t squared is also equal to 0. So we're looking for the intercept, the vertical intercept of this graph. And that vertical intercept happens right there. And what number is that?
6.5.
How do you know? Where does that 6.5 come from?
Well, each tick mark is an increment of 0.5.
All right, so if we're reading on the graph, it looks an awful lot like 6.5. So the graphical manifestation of that initial height is that it's right there. It's where this graph intersects with the vertical axis. What about from our equation? We've got to be able to use that equation somehow. Which portion of this equation is giving away the initial height? Well, take a look at our model equation. Which portion of our model equation down here is the initial height? H naught, right? Looking back at the original statement of the problem, h sub 0 was the initial height of the object. So that's which part of the model equation gives us the initial height. Now, what does that match up with in our regression equation? What number? The number that's just a constant, right? The number that doesn't have a variable attached to it on the right-hand side, the 6.543. In other words, that's where we find our initial height. That the vertical intercept of our model equation, so remember, in our model equation, this h was playing the role of y, this minus g over 2 is playing the role of the slope m, t squared is playing the role of x, and then h naught is playing the role of b. Right? The initial height is playing the role of b. And therefore, when our line of best fit has found us a b, that b is equal to h naught. So the initial height from which this object was dropped must be the value of that intercept, 6.543 meters. We can also, of course, find that same initial height on our untransformed graph. When time is equal to 0, in our original data, that initial height is, again, the vertical intercept, 6.543 meters. So that's for the initial height. The intercept is telling us that initial height, again, because of the relationship between the intercept of our linearized equation and the initial height in our model equation. Those correspond to one another. Now let's unpack the slope. So let's figure out what the slope is telling us here. First of all, what is the slope of my model equation written in blue here? Where do I find the slope?
Next to the t squared.
Next to the t squared, next to our independent variable. And the independent variable on our transformed graph is t squared. So the slope, minus 0.8695. Let's figure out what that means. So which portion of the model equation, if this is my slope, then what does that correspond to in our model equation? Corresponds to that piece. That constant which is next to the t squared, the constant which is a coefficient of our independent transformed variable t squared. So let me make some room here. And let's figure out what that means. So matching up the slope from our linearized equation with the coefficient of t squared in our model equation, we can now be assured that minus 0.8695 is equal to minus g over 2. Because the former is the slope of our linearized equation, and the latter is the coefficient of t squared in our model equation. So we're just matching up piece by piece the linearized equation that we got for best fit and the model equation that we started with. And by matching up minus 0.8695 with minus g over 2, we can now figure out an answer to this final question on here, what is the value of the acceleration due to gravity on the moon, just by solving this equation for g. What do I have to do to solve that equation for g? Yeah, let's just multiply on both sides by -2. Multiplying by -2 will give me g on the right-hand side, and on the left-hand side, minus 0.8695 times -2, 1.739. Okay, we're going to want to put some units on this in a second, but for now, that's how we got the value. By matching up the slope of the model equation with the slope that we found of the linearized equation, we can solve for the value of g, which is what we were interested in here. What is the value of g on the moon? And that just came from matching up the two slopes. Now I just want to know, what are the units of that slope going to be? The units of my g.
It'd still be meters per second.
Meters per second? Well, let's take a look. Meters per second squared. Let's verify that. So on our transformed axes, what are the units on the vertical axis? My vertical axis was a measurement of height. So the units on my vertical axis are meters. Meanwhile, what about my horizontal axis? On my horizontal axis, I had t squared. So what are the units in my horizontal variable here? Seconds squared, exactly. And now, how do you, on any linear graph, get units for the slope? Because the slope is a rise over a run. The units are going to be the units of the rise divided by the units of the run. In other words, the vertical units divided by the horizontal units. So sure enough, this number, negative 0.8695, that number has units of meters per second squared. And so over here in our equation that we solved to find g, meters per second squared was the units of minus 0.8695. And when I multiply that by -2, those units stay the same. And so an answer to the question, what is the acceleration due to gravity on the moon according to this data, is that the acceleration due to gravity on the moon is about 1.739 meters per second squared. That's what the data is telling us. Actual observed values vary a little bit, but this is what the set of data that we started with is telling us. So what were the steps that we did to get to where we got? So we took our data and we plotted it. I mean, you don't always have to do that, but this sort of gave us a clue that this data is not by itself linear. T versus h was not very linear. But taking a look at our model equation up here, I'm going to recopy that. H equals minus g over 2 t squared plus h naught. By looking at this equation, we could make a reasonable guess that because our variables are h and t, let's start with that. That much we know. That's what we have observations of in our data. Our variables are h and t. But because t versus h was not linear, we decided to think of, instead of t versus h, to think of t squared versus h. So to include that square as part of the expression which defines our independent variable. And if we treat t squared and h as our independent and dependent expressions, then we do get something linear, because the model equation now fits the format y equals mx plus b. But in fitting that format, we make the requirement that whatever the slope of that linearized equation is, that slope is going to match up with the quantity minus g over 2. And whatever the intercept of that equation is going to match up with the quantity h naught. And once we know that, then all we had to do was take our data and find a linear equation which matches the transformed data as well as possible. And this is the one step that we didn't see because it was done inside of the app that we used. But the step that we didn't see was that instead of plotting t versus h on that plot on the right, what instead was done was a plot of t squared versus h. In other words, it took each one of these values for t and it squared it. So 1 squared becomes 1, 1.5 squared is 2.25, 2.5 squared is 6.25. And instead of plotting t versus h, what's plotted on that second set of axes is t squared versus h. So this is the data set that was really plotted. And this is the data set that turns out to be linear. So from this plot, from that linear regression that was done, we ended up with this line of best fit, which had the form y equals negative point. So we got a line of best fit, and it had this form, and all we had to do to interpret what this was telling us is just to translate everything back into the context that it originated in. So our y's were really h's, our x's were really t squareds. Then our slope was really minus g over 2, and our intercept was really h naught. See how that works out? Because of how we matched up our model equation to its linearized form over here on the left, that tells us how to interpret everything that's come out on the right. And we can use that correspondence to then find out what is the value of g in this model and what is the value of h naught in this model, just by solving for the relevant parameters.